Okay, so welcome to this second lecture of antenna technology. And today, just before we start, I should just inform you that Canvas has opened its first quiz, and in the end of this lecture, we will look at that quiz, so you know what you should do there. And you will have 1 week to do that quiz. Otherwise, before I start, has it been any questions, any practical questions about the course? No. And if there is something during the lecture, as I also said on the exercise yesterday, try to be active. Use this raise your hand or write on the chat, and anything, so it can be comments that you have, something I should explain better, and so on. So just try to engage into the lectures there. Okay, so then we will start. So some things that we did last week, or not last week, last lectures, we introduced some of the parameters that we are looking at. And first of all, the fields that we have. So we looked at the electric fields here, the electric intensity typically. We had some radiation intensity, a little bit about the Poynting vector that really describes how the power is moving on these fields. A little bit about plane waves, which is what's propagate, especially when we have receiving antennas. We typically think that that is what comes towards the antenna. And then we looked at some antenna parameters here, so directivity, gain, efficiency, input impedance, reflection coefficient. So now you should have some idea what these parameters are. The same with the Friis equation, where these are used. And these were also what was on the exercise that we had yesterday. And in the course, it's extremely important that you do these exercises. So really go through them every week that we have them. And these problems that you have on the exercises are very similar to what comes on the final exam. So if you do the problems on the exercises, you will do good on this in this course. So try to do that, and they really say what are the things that you should know from what we have been doing this week. And the same thing are now that we are down here, and then we open this quiz for this week. So the quiz that now opens today then covers the material that we've been doing this week. And I will come back to that, as I said, in the end of the lecture, and also show you one of the quizzes. And you get then 3 bonus points if you do all the quizzes this quarter, and you can use those on the exam in January, but not on retake exams. So now we are down here, and then we will move on. So what we will look at now is how we actually determine this radiated field. So on lecture 1, there I said that we had like this dipole antenna, and it radiates some radiation intensity comes out, and we can describe it with some parameters. But how do I determine what the directivity is, for example, from a dipole? And the way of doing this is to really say that there are currents here flowing on this dipole, and the movement of those currents, that's charge that are accelerated forward and back, that cause this electric field to radiate. So the currents are really the source of the radiated field. And that means that we will say that there is a current or current density on the structure, and we will determine the radiated field. And then we will start looking at some antennas. So we will look at dipole antennas and typical properties of these dipole antennas. So for example, what is the directivity of a dipole, and so on. That's what we will do today. So yeah, the overview in the same way. I will skip that. So the idea now with these antennas, or analyzing these transmitting antennas, is that we have our antenna, for example, dipole that we have here. And to the antenna, which is the part typically we think out here, which is the radiating element. This is a matching element, or this is a transmission line. We connect the antenna to some feed that we can supply a signal on, or supply some power to. So this piece here is connected to some, say, an amplifier or something that generates our fields. They are coming out here in the coaxial cable. They come to the antenna. They shouldn't bounce back, and then they should create a current here, and the current radiates. That is the basic idea of an antenna. And this time varying currents then that sits outside here of the antenna, that means that electrons are accelerated. They typically move forward and back like this. And when the electrons move forward and back like this, they produce an electromagnetic field. And that creates these radiating electromagnetic fields. On the computer lab that we start next week, then you will actually do this yourself. So there we will simulate these antennas. So we will see the current on the structure and we will see what the radiated field is. Today we're going to do that by paper and pen. So that's the way we will do this part. So the analysis and then the computation of this radiated field consists of two parts. First, we have to determine the induced currents. So the current that sits on the structure outside here. And in the second part, we have to take that current and determine the radiated field. And in the beginning now, and in most of the things that we are doing, we will take point 1 here as something which is, call it like an educated guess or experience. So we will actually say what the current is. We will not compute the current. But we will do part 2 that say we have this current, how does the current radiate? And in general, it's actually pretty hard to determine the currents on the structure. To do that accurately is very hard by paper and pen. And this is one of the reasons why we have this computer software. They can actually determine the currents very easily and very accurately, because you do that by solving a huge linear system, so matrix equation. And you know from yourself that matrices, you know what it is, you can solve matrix equations, but you're also well aware with that when you have more than 2 or 3 unknowns, it's kind of tedious. You want to put it into MATLAB and solve it, which means that you leave it to the computer to do it. And that is what's happening in this software that's doing these computations. Also with the software FECO that we will use both in the computer exercise and in the labs, I will give some instructions to that and talk a little bit more of it in the end of this lecture, because you can run it also on your own PC. So we will set that up there, but I will come back to that. So we will then start with our dipole antennas. So before we compute this, let's understand how the current looks like on this dipole and what we should compute from it. So the first one we have, I know the picture here is pretty small for you. This is the dipole I'm holding in my hand at the moment. And that's the one that you see here. It's actually the same antenna. And that is a dipole antenna. This is another dipole antenna that we have here. And this is a third dipole antenna. When you just look at them, you can see that they look kind of different. And then you can ask what is different with these ones. And what is really different with them is the feed. So in this case, you have a coaxial cable that comes here. And then what you get is that it produces a current that goes here. So here your current flows forward and back. And that gives this acceleration of these charges, which creates the radiation. If you take these ones, it's the same thing. The charges are accelerated here, forward and back on this structure. But your coaxial cable in this one and this one comes here. So it's a different way of feeding this structure. The ones that are to the left are typically called a sleeved dipole. And this is a regular dipole, but it has something that's called a balloon here. I will come back to that. And that has to do with taking the waves that goes on the transmission line, the coaxial cable, to this dipole. And balloon stands for balanced to unbalanced. And a coaxial cable is considered unbalanced and the dipole is balanced. So that's a detail in the feeding, which we actually will talk about next week. On this week, we'll only do one thing, and that is what we say here is that you have typically current density, and in one approximation, the amplitude looks like this. It looks like a cosine a sine function. So the current density that you have here as a function of the position of the dipole is strongest close to the center. So here is the opening of it, and it's 0 out at the edges that sits here. Here the current approaches 0. And that means it's the same thing that sits on this one. So it's 0 up here, it's 0 down there, and it's strongest at the feed point. And in the beginning now, what we will do typically, especially today, is that what sits here that we will not really think about. And in the same way, what then comes here as a feed to this one, these parts we will not really neglect in some ways. We will only look at this radiating part of the structure, which is the dipole that sits up there. And if you look at it now, it means that these two dipoles are the same. So in that way, we will look at the radiation from this linear piece of wire and how it radiates. That's what we're going to do. And that's what I'm doing. Okay, so where do you find dipole antennas? I will say almost everywhere. It's the most common antenna. It's the easiest antenna for us to understand, but it's also really, really good antenna. And one common case is that you go home and you look at your Wi-Fi router. Many of them have these kind of little antennas sticking up. In most cases, it's called a monopole, but they are in most cases not the monopole, they're actually dipole. And they are this sleeved dipole, where you can see here, you can see the wire sticking up. And if you were drawing the rest of this picture here, you will actually have metal going down also there. So you will have a dipole with a current looking around this structure. What you have here is the end of the coaxial cable, really, really tiny open coaxial cable, a diameter of approximately 1 millimeter, and that's connected to the electronics and to the signals that can be transmitted. So these are very, very common antennas, and they're used for many different things. They exist almost everywhere, I would say, dipole antennas. So thinking about those a little bit more, we will just motivate them how they can come in and how we will look at them. One way of looking at this is that you have what's called a twin wire, the transmission line that sits here. So you have two wires, and these wires could carry some current. And if you send a wave on these ones and it just terminated here, it's basically reflected back. So this is a transmission line as a circuit. And this will be an open circuit transmission line with a total reflection. So everything is reflected back. The characteristic impedance for this one can be calculated. It's a known number. We will come back to that one also next week. In the course, we are not going to calculate these things. It's just something that is known and given. And the open-ended transmission line have a reflection coefficient of 1, which is due to these open terminals in the transmission line. So signal comes there, signal is reflected back, which means it doesn't radiate. It's not an antenna. And now we can try to remake this to an antenna. And one way of doing it is to take your twin wire and then you bend the wires here. You bend this wire, you bend this wire. And then you have your dipole antenna here that has length L. And then you hope that this radiates better in some ways. And then what we do is what we said before, is that in the end of these ones, if you think about the circuit, it comes a current. At the end of this wire, the current cannot disappear. So the current has to approach 0 up here. And in the bottom of it, it has to also disappear. And then a reasonable assumption here is that you have kind of a smooth distribution of this current. And it looks like a cosine function with its maximum in the middle here. And what we do now is that we also remove entirely the feed, especially as I said, with showing the pictures of the dipole. And I just say that here it sits a voltage. So this one is fed by some voltage. And this voltage represents everything that would happen here by this twin wire that comes into it. So we make a simplified model of these ones. And it's a very good way of doing it because it means that the impedance that I have here, said input impedance to the antenna, models the antenna seen from the transmission line and circuits, and what's outside of it takes care of the radiation. So this is the model we have. And then comes the question, what do I need to do now? I need to determine what the electric field is somewhere here. Now I want to determine the electric field, and the electric field is created by this current. So I need to do this. This is what we need to do. That's our big question of all of this. And it's really the fundamental part we now have in the beginning of this course. How do we determine what the antenna radiates? What is the radiation from this antenna? You have a current. The current produces an electric field. I want to know what this electric field is. which means I need to compute it. You need to compute it. And in this course and after the course, you should be able to compute what the radiated field is from an antenna when you know what the current is. That's a typical knowledge you should have. And it's really one of the basic knowledge that we have in the course. And it's very important to know it. You should really know it both for the course, to get past the final, to do the exercises. And it's a problem that typically comes on the exams of these ones. So it's really one of the fundamental parts that sits there. And that's what we're going to go through in this lecture. I'm going to motivate the formulas that we have, so you understand what the formulas are, and then you're going to learn how to use them. So you should both understand and interpret the formula, and you should be able to use the formula. That's the goal of what we are doing. So that means that we will look at this current, and now I talk about the far field, so I will define what the far field is. So what is the far field? That is that the radiation from an antenna can in general be very complex. So if we have an antenna here, so this is the picture of antenna, in this case a very big antenna, here is a parabolic reflector, then I can be at different distances from my antenna. And when you're very close to your antenna, you are in a region here which is called this reactive near field, this region here. And that is what you sit next to your antenna. That is what's happening when you take your cell phone or your antenna and you put it next to your head. If you run this case, so think about your cell phone, you put it next to your head, you run it at say 1 gigahertz or 900 megahertz, you learn what the wavelength is for 1 gigahertz. How long was it? You all should know it, it's 3 decimeters, basically this. Which means that if I put my antenna here, my head is within 1 wavelength from this structure. That is called the reactive near field. That is what's producing these things of SAR, specific absorption rate, which we will talk about later, which means that we have restrictions of how much power can be transmitted close to a head, for example, because our head will absorb this and eventually get warm. And it can, in some ways, injure us if the power is too high. And every device that is sold is forced to satisfy regulation, which means that the power has to be sufficiently low, so it's entirely not dangerous for us. So that is what is SARS, it's standardized. And that is because we sit so close to it. Then we go to the reactive near field, and that means that you move away further from it. So now I'm a little bit away of this one, so I'm sitting somewhere here. But you're not far enough away from your structure. You are far enough to be away from this field that can pump like this, but you are not far enough to be able to say that different pieces of the antennas are in some ways, you can distinguish them in some ways. So the antenna doesn't have a given radiation pattern anymore. It is in a mixed region in some ways. And then when you go outside of this, so you move even further away, so you're sitting outside here, then you are in this far field region, this region here. That's where we will be in this course. So we will move away, so far away from the antenna. So in some ways, we only distinguish different parts of antenna with the distance to that part of the antenna. We don't get an angular resolution, basically, of our antenna. If we will see it, it would look like 1 point. And it has only one thing that's called a radiation pattern. The distance to this one is typically given by something that stands down here. That is just a consensus that we say that we should be at the distance that is larger than 2 times the dimension. And the dimension is now the d that sits there. So you square that number, and then you divide by the wavelength that you have here. Takes 2 times this one, and that gives a distance. You can see the unit of this one is meter. D is measured in meters, wavelength is meter. So meter squared over meter, and you get a distance. And what that means is that the phase doesn't affect it in a very complicated way. It's a very simple way it affects it. And that simplifies a lot of the analysis, and it means that these quantities like the gain and the directivity, those quantities are defined because they are far field quantities, and they only depends on the angle. So if I have this antenna, I get some radiation intensity there, 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 and there. And it only depends on the angles that it's there. If I measure the angles from one piece, I get this value. The decay when you go out here is given, so the electric field decays as 1 over r, and the power density decays as 1 over r2, what we talked about on the last lecture. That is in this far field region. So that is where we actually sit in this course. So we will use that one. We will talk a little bit about these ones because they are needed, for example, for the SAR and so on. But most of the things we're doing are really here, and it simplifies things a lot. So then we're going to determine now our dipole. So again, go back to our dipole. This is the long piece. I drew before that the current density looked like a cosine function around here. We just assume it is like this. We can validate it against solutions of Maxwell's equations. But here we say, okay, it looks like this. And now I'm going to say, how does this current radiate? And if we think what's happening here is that we have now a dipole, so a long wire here, it has some length L. And if I'm sitting here and I'm going to determine the contribution from this field to my receiver point, so this is my Rx that sits up there. Then, of course, the current that sits down here contribute, and it contributes basically with a distance that comes from there to there. The current that comes from up here contributes with a distance from there to there, and the currents from there contribute with the distance that current has. And in the far field, the only thing that's important is really the distance from the current to the observer point. That's the only thing that comes in these cases. And that is what we're going to use to determine this radiated field from this structure. So to do this, we actually say that don't think about this entire current. Divide the current into small pieces. This is exactly what's done in the computer when the computer solves this. But it even is sitting in our way of thinking and analysis of it. So instead of saying that this is a dipole, which is very long, we say that let's treat the radiation from this one separately, the radiation from the current that sits here separately, there separately, and then I want the field, and then I just take the sum of all of those ones. So we can sum up all of those contributions. So I write the sum over all of these contributions from the different pieces of this. And then I get the total field. And that's how we're going to determine what is radiated. So that's, yeah, precisely what I said there. We sum up the total radiated field as a sum of the radiated field from each small part. And they have then different spatial positions. So what we need to do is to determine what is the field when something is radiated from one point and then when it's radiated from another point. How do we add those up? And then we see to know, what do we know about electric fields? Because now they propagate from different positions of these ones. The dipole is like half a wavelength long if it's a half wavelength dipole. So the distance is quite long. And think about this when you now hear a wavelength and half a wavelength. What does that matter for phase? Think about the wavelengths. That is in some ways that you go from 0 up to pi and then down to like 2 pi and then you're back where you started. So one wavelength is 2 pi in phase, and that means half a wavelength is pi, 180 degrees, which means that the phase difference that it can come in here can be quite big. We cannot neglect it, and that is what gives the radiation pattern. So to understand that, what we know is that the electromagnetic waves, they propagate with a given speed here, approximately 3 times 10 to the power 8 meters per second. And that means to propagate a certain distance r here, it takes a time t, and now it says d over r there. So obviously you say r there. And that means I know how long time it takes. And then I ask a question, what does that mean? Because it takes a time to propagate. But we also have said that we typically use time harmonic signals here. So we will say if we are at 1 gigahertz or 2 gigahertz or 3 gigahertz. What does then a time delay or a time shift means in the frequency domain? That you have all done. You recognize it from many of your earlier courses. And if you take the Fourier transform of a time shifted signal, So we say here that Fourier transform of f is capital F here. If I now time shift this signal, so I delay it with the time capital T here, then I should take the Fourier transform of this one. I can change the variables. And then I can show that this is the same as taking the original Fourier transform and multiplying it with a phase factor. So if I have an antenna now where my receiver actually physically is closer to this point than this point, for example, the receiver is up here, I'm closer to this one and this one, then it takes shorter time to go from there to there than here to here. I need to compensate for that time shift. And I do that compensation by taking care of the phase that comes in. So that's what I need to compensate with. And now we will rewrite this. And again, I can see that I mix my R's and D's. So then I take and rewrite these ones. So I know that I have here my T, which is R over Z0. So I put in my T here, it's an R over Z0. And then the angular frequency divided by the speed of light is the wave number. So that means that the phase shift I get of these signals is proportional to the distance R and multiplied by the wave number K. That's what I need to do. And here I get these wave numbers and spatial distance because I'm talking about the physical distance, and I'm not talking really about signals that are changing in time in the same way. I'm really living in space here, but it looks very much the same. And what I then need to do is to determine the electric field from a position. So if I have my current here, it depends on different positions. So I have one current here, I have another current here, another current here. I need to determine what those are and then determine the distance from those positions to my receiver point. That's what I need to do. I need to compute that distance all the time. And we will now do that in a slightly simplified way. So let's take away this. So let's take an example of this. So let's say now that I have a dipole again. So think about this one. And I take just two positions on it. And I say that one signal is generated at same time 0 here and time 0 here. And I draw that here that this is one position where I have my current. This is another one. And this is now at time equal to 1. And it means that the signal has gone from here to here, basically. And then I want to know what is the signal at position R1 and R2. That's what I'm curious about. So if I let this go, if I wait a little bit longer, the wave will propagate here much faster in reality because it goes with the speed of light. But you can see I go 1 unit in time forward, then this moves 1 unit of space outwards. And in 3D, it moves on the sphere. So it's a spherical shell, it's moving away. The same distance from the source points, it just moves away. And move to time 3, times 4, and times 5. And then I can see that when I'm sitting at the receiver here, my physical distance from this point and this point are the same. And that means that those signals will reach this point at the same time, and I can add them up because both comes at the same time, which means that they have the same phase. So this is constructive interference. I get just to add those two basically. Then if I go on here, and then I could see I had already, the blue one has passed R2. And when I move up basically to time t equal to 9, then I get this one to also come to R2. And that means that typically these signals will now have different phase. Now I assumed from the beginning that this had the same phase, but it doesn't really matter in these cases. What it says is that different distances to an observer point should be weighted with its own phase. And actually that is giving you the radiation pattern. It's everything that sits in the radiation pattern. And this is the physical understanding of the formula that we will see very soon. That is what comes in there. So when you think about it and you see your little dipole here, the reason why you can get the radiation pattern here will depend on two things. One is that the electric field has a polarization and the current goes in the direction here. The next thing is that the distance to different pieces of this are different. And maybe that the phase that's transmitted from different pieces have a different phase. That will give you your entire radiation pattern. That is what comes in. This is the underlying factor to this. So what is then the distance from one point to another? So then we need to compute the distance. I mean, that's what all of this says. It's very important to know what the distance is between the antenna and the receiver, and not only the center of the antenna, every position on the antenna to the receiver. I can actually resolve that distance then. So I need to know what the distance is. So let's compute the distance. What is the distance here between a point, what to say here, r minus r prime? So let's say that we have a coordinate system, and this is the center or the origo of the coordinate system. I have here, I will have a receiver. So say here is my Rx, and let's say here is one part of my Tx. The Tx can sit in many positions. And then I need to know the distance between the Rx and the Tx. How long time does it take the signal to propagate them? So if we compute that, we know that we can write the distance as a square root of the basically the product of these two terms. And if I have now r minus r prime and basically the square, so I multiply it with itself and we take the scalar product, it gives this as r2, and then we have the inner product between these two, and then I have the length of this distribution that sits there. This is just an identity. And now I write everything with scalar products to do this. And then what we will say, that is that we are far away from our antenna. What does that mean in practice? It means that this is my antenna that sits here. So think again at this dipole. This one is a few centimeters long here. And then you are like 100 meters away from this one. So it means that this dimension here of the dipole is very small to the distance you are away from it. That was precisely the formula we had in this far field distance. That has to be far away in these cases. And if I now write this up, it means that the r here, the distance from there to there, is a very large number. I can pull it out. And then if I take this distance here, r prime, I divide by r. This is a very small number, so I can skip it. And this is something that still will contribute. And now I pulled out my r of this one. And then I use a Taylor series approximation of this square root. So I still have the dominant term here. This is a small term, but it still contributes. And then I get a term here, which is actually in some ways linear in this r prime. And now this will give me the way the phase and time delay is shifting when I move between different points. So I multiply in this r again, and I can say I have one term, which is just r, that's the distance. And this is a correction term to this r. You could write it as a length of this r prime here, if you want, time cosine phi. That's what we have in. And if we take an interpretation of this, so let's look at the picture that we have down here. We can see that what it says is that when we are far away, it means that the distance here are almost the same. So that distance and that distance are almost the same. And we get only a shift that sits down in these lower pieces, which is what we have here. So it is that we have to project this r prime, the position to our source of the antenna, in on the direction where we are looking. That is this inner product that we have to take between this direction r hat and r prime. And r hat here is the vector that points away from this one. So this is my r hat. It has length 1 and it points in this direction. And that is what I should know what this distance is. If I know that, I can calculate this distance. So the time delays now become a phase factor in the frequency domain. So I can plug it in. I have this distance I should have in my phase. I approximate it because I'm far away. And I get first one term here, which only depends on the coordinate system and the observation point, which as this would just oscillate quite a lot. And then I have one thing that only depends on the source and the direction of the observation point. So the direction to your receiver. But it doesn't depend on how far your receiver is. It's only the direction to it. And this is the important term that will come in. That is the term that we will use to determine this one. If you see that one, does it look like something? Something you recognize? What's the shape of this one? It actually looks like the term you have inside of a Fourier transform. And here it will actually show up that we should take the Fourier transform of our currents to get the far field. So the distance here, it changes with this r hat times this r prime, and it creates this phase shift. That's what we want to have. So this is now the interpretation that the change of distance gives a change of propagation time or a phase shift of the signals. And we need to compensate for this one when we determine the radiated field. An interpretation now is that we say that we sit with our dipole. So let's say this is a dipole, and then it means that you would have a current here on this line. So think about your dipole again here, and look now in this direction from the dipole. What does that mean on the observation point of this one? If I sit here, you all see that it's slightly further away to that point and then that point. It's always closer to go to the center here. But when I move this point further and further away here, this is always true, but the distance here actually approaches 0. So when you go in that direction, you have your dipole here, and I'm looking in this direction away from it in this plane. It's the same distance to all of these points. But when I take this once and I say I put a slope on it instead, I still go in this direction. Then, of course, the point that sits upside here is always a little bit closer to my, say, receiver point that sits there. And that means that the signal on this one that's transmitted from this point reach that point slightly before the signal that's transmitted from here. And that will produce your radiation pattern. So there we get in this distance that we have to measure. And that means that we can get this radiation pattern from these dipoles. And I said, this is one part of it. The next one will come that the current actually have a direction. And that's a dominant term for small structures. So now we're actually ready. Now we can compute the radiated field from a given current. That's the core of this. That's what we want to reach. Everything I've been doing now has been to motivate this formula. For you, this will be the most important formula that you actually have, I would say, in this course, in some ways, to do this, and these first weeks, especially to solve the problems. That is the formula we need. And the way you should use it is not that you should say, okay, this is a formula. I take the formula from the formula sheet and I learn how to calculate it. No, you should actually have learned the interpretation of it. Why does this look? What does this formula tell us? So what we could see in this, that we needed in some ways to add a weight that we should determine the radiation pattern here. So a phase term, we are far away from it now. And the phase term was what sits there. The next thing I said is that we should add up the currents from all our structures by dividing it into small pieces and summing it up. A sum is an integral. So we should integrate this. That's what we have there. You should take your current density, you should weight it with this phase factor, and you should just sum up all contributions from the current. And when you do this, you observe the fantastical thing here. What you have here is precisely a Fourier transform. In some ways, just by chance. It just happens to be like that. And you all know Fourier transforms. You use them in so many courses. So whatever you know about the Fourier transform, you can apply it to this thing here. But you have to apply it to the current density. You don't apply it to a signal that's changing in time. Here you apply it to the current and how the current or current density is changing in space. That's where you apply it. And you take the Fourier transform of that. And this gives us now a quantity, which we'll call the radiation vector. So that is this F here. And you can see that the F depends on the parameter that we have here, which is this R hat. And that is the same thing as those two as we have here. It's just a way to describe these angles. So here I sit now in the spherical coordinates. I will come back to the spherical coordinates very soon. We will do a lot of them. You all have seen them before. You might have forgotten pieces about them. We will come back to all of these pieces. But it means that you have your antenna here. And what you say is that how does this antenna radiate in this direction? How does it radiate in this direction? How does it radiate in this direction? The direction is this theta and phi. And the current is going on this dipole, and you want to know how it radiates its power. That is given by this radiation vector, of course. The radiation vector gives the E field, and then the square of the E field gives the power that becomes radiated. So these are the quantities that we have. So I mean, this is good. I mean, why do we make such a big fuss of it? We have the current, take the Fourier transform, you get the field. Yeah, that's what we do. But we should, of course, understand why we do these things. It should not be just a magical formula. You should interpret it. And then it comes one more thing. And that is one thing that we know. And that is, what is actually the field far away from its source? And now I have just taken this one, and I've taken the Fourier transform of it. So assume now that the current goes straight up here on your dipole. That means it will point in my coordinate system in the Z direction. Does that mean that my electric field always points in the Z direction? No, it doesn't. And the one thing there that we know about these electric fields is that far away of these ones, they propagate basically as a plane wave. And in that wave, we have this right-hand rule, these things down here. That we know that the electric field is perpendicular to the magnetic field, is perpendicular to the propagation of radiation, so the direction of the power flow. So if you take your hand here, and if you, in this case, would put here that this is the electric field, this is the magnetic field, this will be where your pointing vector is pointing. And in our case here, this S is proportional to this R hat direction, which means that the power is always propagating away from your antenna. That means that the electric field has to be perpendicular to that one. So we have to add that part. We have to include that part in this. And we do that by taking away this part of it. So here I remove the radial part of it. We just take it away because we know it shouldn't be there. In this, you can see that I'm now doing a derivation of this, which is not entirely strict. I'm not bringing out this numbers that's in front of it here. For you, I would recommend that you can look at it in an appendix to these lecture notes. You can also look in Orphanidis in another book. You can derive this from Maxwell's equations. But to really understand it, that is what I'm doing here. But you can do all the math into that one. But you could get the intuition and understanding of it by actually thinking about this time difference, which I think actually for you is more powerful in this case. So the far field in the general case here is determined from the Fourier transform of the current density and removal of the radial component. That is the key part that we have. That is how we get the radiated field. Now we're going to do that for quite a few antennas. So before we will do a poll on these ones. So we will start one here. And you can see the questions that sits here. That the far field here is determined. Oh, now you cannot see that. Okay, that was clumsy on me. I will take that away first, so we go back. So the question here is, the far field is determined from the Fourier transform of the current density and removal of the radial component. And now is the question, why is the radial component removed from this radiation vector F, which means that we take F, we subtract what goes in the radial direction. And there are three alternatives here. One is that the E, H, and R hat are perpendicular in the far field. B, that the field can locally be approximated as a plane wave, propagating this R hat direction. The C one is that you can use Maxwell's equation using what's called vector potentials and show that the electric field can be written as R hat cross product, F cross product R, far away from the sources. That is the question what we have. And we have the perfect time to actually do this now. So what do you think? Which statement or which statements are true in this case? So take and fill that out, and then we discuss it, and then we will take a break. Okay, we need a little bit for more people to vote. I've got 7 people in so far. Yes, believe it. Fill in what you think. Okay, so maybe we'll stop there. We get 14 answers. And I think you can see the answers here. You can see that they are quite equal in some ways, slightly more on A, a little bit less than B, and a little bit less on C. All of them had more than 50%, which is very good. So then you can ask the question, which one is actually correct here? All of them are correct. These are just different interpretations of the same thing. And this is an incredibly important thing for you to understand, that this is a property that we have of this electromagnetic field. This is a property that we have of radiating antennas. And A, B, C in these cases are only different ways to argue or convince you that they are the same thing. C down here is, of course, the most strict version of doing it, because you really mathematically show this and what the assumptions are. It requires, of course, more, what I would say, vector analysis, electromagnetics to do it. A and B are much more physically intuitive in some ways. They almost say the same thing. But this is a part that you should really understand, that when you have your antenna, you go far away from it. Look at, you are sitting at your receiver, you have your electric field here. Yeah, put your, well, like the thumb in the direction away from your antenna. Yeah, then the E and H fields will be in that plane that goes around when you use your right hand rule. They have to point in that direction. And this is, of course, valid from wherever you are around these ones. You just have to turn it around. Maybe it's hard to do it with your hand. But the energy propagates away from this one. And the electric and magnetic fields are perpendicular from that direction. That's a fundamental factor. And if you have that understanding, and you have the understanding of this time delay that gives this formula, that's exactly what we need. That is the part of Maxwell's equations that we really need in this course to determine fortunes. So that is important, very important in this case. Okay, we will take a short break now. So we will reconvene.